So can you hear me?
Or can you hear me without the mic? That would be easy. No.
I hate mics. So first of all, of course, thanks to the organizers for inviting me here and organizing this wonderful event. I will try not to bore you too much over the course of the next 4.5 hours. Hopefully you won't kill me in the process. And you might even learn something, so we'll be okay. So to start off, a little bit of bibliography. I'm going to be following, I was strongly inspired, let's say, by the Dynamical Processes book, which is now a little bit old, but it still does a very good job of describing all the fundamentals and all the important techniques, especially analytically. And a couple of more recent papers, one that this is actually a book chapter, one that I actually helped write, and then one by Alex, which does a very good job also of doing an overview of how to model these type of processes and recent developments. So to start off, I'm going to talk to you a little bit about complex networks. As you know, if you're here, you probably know this already, but it's always good to start at the beginning, so to speak. See if I can actually see this. Right? Yes. So what I'm showing you here is a bunch of examples of networks. So we have the internet over there. You have a trophic network in a lake. So each node represents some type of microscopic animal that's eating each other. Here you have the yeast interaction network. Here you have an actual neural network with actual neurons. And here you have the power grid network of the US. And of course, everybody's favorite, so the complex network, the social network of Facebook. Right? And while there, each node represents a person, and each link represents a connection between people. So moving on, I'm going to talk to you. Here we go. And of course, you've heard of this idea of big data, which of course has gotten a lot of attention in the last few years. When I first started talking about these things, I only had like 2 or 3 covers in this slide. I keep having to make room for more. And of course, the reason is obvious. Right? More and more data is being generated, and of course, more and more interest in how we can use this data and learn about this data and use this to create and extract information and products and systems is ever increasing. And this goes, of course, from science and nature and Time magazine, popular science, popular mechanics, futurists. There's the economists hiding over there, competing in science and engineering, etc. And this, of course, is because it's creating a huge number of opportunities and challenges. Right? Opportunities because it's allowing us for the first time to observe things that couldn't be observed before, but also challenges because you need to create new tools and new techniques in order to analyze all of these data and be able to extract information from all of these data. Especially because now we start having increasingly larger systems, and there you have to start getting newer techniques and newer ideas. But of course, you still need the fundamentals, and what I'm going to talk to you today is mostly about the fundamentals. So, and here we have a real example. So this is an actual empirical network. Each node represents, I believe, an author in TRL, and 2 authors are connected if they author the paper together. And what we're seeing here is basically a diffusion process, let's say, on this network. Right? You're starting with some piece of information or some tag in one node, and then this information is getting spread from node to node. The colors go from white to red, I believe, yes. Representing time, so you can see, so the redder it is, the later in the process it got information, so these are very, very late. The white ones should be somewhere over there, if I'm not mistaken. And the blue ones, of course, are the ones that never received it. And this, of course, in this case, since it's a very simple process, and each node just gives the information to all nodes in its neighborhood, if you wait long enough, everybody will receive it if it's a connected network. We'll see that in detail in a second. Now, one of the points I'm trying to make here, and I always like, whenever I can, I try to use visualizations and visual images to explain things, is that you see immediately, just by looking at it here, you see very strong correlations and details, right? You see that it starts usually it will start in a little dot over there, and then you immediately start and jump to very different areas of the network. You will see that the colors also the colors, yes, also match well with the degrees. So here the degree is represented by the size of the node. So you see that nodes of similar sizes tend to have similar colors, or at least similar ranges of color. And what this means is that the way your likelihood of getting this information or getting touched by this process correlates strongly with your degrees. So the more central you are, the larger your degree, the earlier you get it in the network. Well, if you look for the red nodes, they're all the tiny little ones hiding in the periphery. They're not well connected, so they take longer to receive. And of course, I'll show you all of this in analytical detail. Now, before we do this, let's start a little in the actual beginning of time and talk a little bit about graph. Of course, you've probably already heard all of these things, but I like to make my definitions clear and make sure everybody is on the same page. So here is my favorite network. It's tiny and it's well understood, and of course it's easy to represent. So you have only 5 nodes. You can define the adjacency matrix, which is just a simple matrix that has elements 1s or 0s, depending if the node I is going to be node j, then element aij will be 1. If it's nothing like that, it will be 0. Okay? And of course, for this particular network, gives you this matrix, which let's put over there. So now you can define the degree distribution. The degree distribution is basically how many connections each node has. Mathematically, you could calculate this by just multiplying the adjacency matrix by a vector of 1s, or you can just sum over the, which basically corresponds to summing over the length of the matrix. And if the matrix is directed, of course, if you multiply on the right and multiply on the left, you get different values that correspond to the in degree and to the out degree. The definition of the degree distribution is basically, of course, you're just summing all the nodes of. You're just counting how many nodes have degree k, and this gives the distribution of degrees. So it's just the histogram. And you can think of this as being the probability that the randomly chosen node has degree exactly k. Which is a quality, of course, is very important in many contexts. So. Now, of course, every time you have a non-zero entry, it means that there is a connection between them, between two nodes. And this is coming straight from the matrix. But now, of course, in most cases, you're not interested in the direct connections between nodes, because those are obvious and they're given. You're interested in how you go from one node to the other according to some path. Right? So one simple way to do that, so this, if you want to go and find out how many ways you have to go from node I to node k, starting in node I, you can go to node j, because these are the nodes that are connected to y, and then from j you can go to k. But since there's various possibilities of these j, we have to sum over all the j's. Right? And if you remember your linear algebra, what this corresponds to is basically a matrix multiplication. So it's the power of the adjacency matrix. And here you have what happens if you grab that matrix and just square it or multiply it by itself. And you get all that. And basically, each element in this matrix now is how many ways you have to go from node I to node j in k steps, where k is that power you have there. And of course, you can generalize this, and you get the nth power of the matrix. Now, and the reason why I'm basically mentioning this is to make this point, is that the diagonal elements here, if you look at this expression, so PII would be AIJ, AJI, right? And what this means is, how many ways can I come back to where I am in 2 steps? Now, if the matrix is undirected, what this gives you is the degree of the matrix. Because you only have one. Because for each edge, you can go one way, you can come back. Around the same way. So now another interesting quantity is the clustering coefficient, right? So what this gives you is basically how clustered the network is, or in other words, how many of your friends know each other, in a sense. And of course, this will depend very much on the structure of the network and how well connected the network is. And will depend, of course, also on the degree of the node. So nodes with larger degree will have more possible triangles. Right? So this gives you the possible number of pairwise combinations of a node of degree k. This would be basically how many connections between your friends are possible. And then, of course, for those, you measure how many of those actually exist. And so the clustering coefficient is basically PII
3. So this is how many ways can I go from node I back to node I in 3 steps. So if you think in terms of the matrix formalism, this would be the diagonal element of the third power of the matrix. So you can start here, go there, and then come back here. And this divided by the, basically by the number of connections gives you what is the fraction of those edges that actually exist. And if you take the average of this over the entire network, then you have the average degree of the average clustering coefficient of the network. Which of course will vary widely depending very much on the structure of the network and the origin of the network. So social networks tend to be highly clustered. Other types of networks, like technological networks, for instance, are much less clustered because they're more trying to span the system instead of connecting the system. Let's start a little bit with network models. And this, of course, you've heard of these models, but it's a way I like to introduce some of the techniques of the mathematical techniques. And since you already know the model, you can kind of ignore the model part and just focus on the technique part, which is interesting. So let's start with the address ready network, because it's everybody's favorite random network. So it's the simplest one. And here what you have is you start with a bunch of nodes that you throw on the floor, and then you connect each pair of nodes probability. It's as simple as that. This gives you how many edges on average that you have on the network if you repeat this process many times. And of course, the average degree is simply 2 times the number of edges divided by the number of nodes, and it's Pn. So, right, so the higher the probability of you creating each edge, the more edges you have, so the larger the degree will be, the average degree will be. And of course, in the maximum value has to be n minus 1, because each node can only connect to n minus 1 other nodes, and this is usually abbreviated to just be n, which of course doesn't change too much. So if you want to build a network with a given average degree, you can calculate immediately what is the value of p that you need, and here I'm just approximating n minus 1 by n. Now, if you want to find out what is the degree distribution, how we calculate the degree distribution, so you have to make this assumption. So you say for each node of degree k, you have to choose it as the endpoint of 2 connections, and the way to do this is basically by this combination. So you have to, probability p, that node is chosen, it has to be chosen k times, and the probability 1 minus p, it has to not be chosen n minus k minus 1 times. Right? So because you wanted to have exactly k connections. And this factor over here is just giving you what is the basically combinatorial factor of how many times you can do this in how many different ways. Now, if you throw in Stirling's approximation, you can get rid of all these factorials and simplify it a little bit, and you end up with the usual expression everybody knows. And then when you plot it, you get what you expect, which basically means it's a very well-defined distribution. It's very centered around a specific value, which is the average of that degree. You can quantify immediately what are the fluctuations around this degree, so how far you can expect it to go over the average or below the average, or the average that you would expect, the expectation value. Of course, these fluctuations will be relatively small. So it's very unlikely, for instance, that you will find that you generate a network by this process that has an actual measured average degree that is, say, 10 times the expected average, because those fluctuations, that will bring you basically over to this side of the distribution, and you wouldn't see it. It's very, very unlikely. Now, of course, everybody knows that this network is not very realistic. There are many problems with it. Of course, it's mathematically treatable, so this is why people spend a lot of time studying it and trying to understand it. Excuse me. But when people started actually observing real networks, and this was basically at the dawn of this idea of this age of big data, in the late 90s when big data sets and big databases started becoming available, it became clear that this was not a very realistic network topology, right? And so 2 very smart people, Baradaz and Albert, came up with a simple model that will try to reproduce the main features of the empirically observable networks, right? And one of the main features at the time, which was something that made it completely different from the Arthur-Sreni networks that the people had seen before, is this idea of a very broad tail degree distribution. Right? Instead of the degree distribution being well centered in a specific value with not that many fluctuations around it, you actually have this broad tail degree distribution. And the mechanism that they propose for this is something called preferential attachment, and the idea is very simple. You build a network step by step, and now whenever you're trying to decide where you should connect a new node, so each time step you add a node, and then you have to decide who to connect this node to, and you give preference to nodes that already have a high degree. Right? So this is known by different names: preferential attachment, the Matthews process, etc. And or the rich gets richer mechanism. And so the more edges you have, the more likely you are to receive more edges, so you get higher and higher and higher degrees. This, of course, is unfair. Oldest nodes will have tangentially more degree, and hereby oldest just means that they were added to the network in the beginning of the process. In simple cases, of course, the power law, if you'll see that in a second. If you do this process in the simplest way, the way that was first proposed, you end up with something with a power degree distribution of exponent of 3. And of course, younger nodes will always connect to the older nodes. This is by construction. Because every time you add a node, you're connecting it to nodes that already exist. So the old nodes get all the connections from the new nodes. So, and let's see how we can actually calculate this. So our quantity of interest for now that we're going to use to define this process is this funny probability. And this is the probability that a node created a time step S. So here S somehow is the label of the node, if you think that at each time step you add one node. Has degree K at times T plus 1. Right? And this is a very simple example of something I'm going to talk to a bit more in more detail in a second. And so here what I'm saying is if I want to end up with probability with degree K times T plus 1, there's two possibilities. Right? Either at times T, I already have degree K and I do nothing. Or at times T, I have degree K minus 1 and I get one more node, one more link. Right? And this is basically what we're seeing here. Right? So this is the probability that I have degree K at times T. And since I have degree K times T, I don't do anything. Or it's the probability that I have degree K minus 1 times T, and then I get a new link. Of course, the probability of me getting a new link, since it's proportional to the degree that I have at that moment, it's K minus 1 over 2T. Here the 2T is just a normalization factor over the total number of edges in the system. And here you have the converse probability, so it's 1 minus the probability that I would get a new node, a new link. And since T, of course, is and this is where the normalization factor comes. So if you sum over all the degrees, you get 2 times the number of edges, and here I'm assuming that you're adding one node and one edge at each time step, so you get 2T. Now, if you sum over both sides, you can simplify this expression a little bit because you can see this is very unwieldy, and you don't particularly care about each specific node and the degree of each specific node at each point in time. So if you just sum over all the s's over all the nodes on both sides of the equation, you get something like you get this expression, which you can then write in a simplified way by defining a helper function, which is one step closer to the actual distribution you want. Right? Here, what I'm trying to do is I'm trying to calculate what is the degree distribution of the network. I start with something that depends very, very precisely on what node I'm talking about and what degree I'm talking about and what time step I'm talking about. And I'm trying to, from this, to arrive at something that is very generic and gives me only the information you need. Right? So here what I'm doing is I'm basically defining the sum over all S of this P, S, K, T plus 1 to just be this capital T, this large T. Right? And by doing that, by making that definition, you can simplify and arrive at this expression that now does not depend on S. Right? So I already eliminated one of the variables that was getting in the way. Yeah, and so here is the definition. And now you can say, okay, but I don't care exactly about when things are happening, because this is not real time, this is just model time on how I'm building the network. So let's see what happens when I take t to infinity. In this case, of course, taking t to infinity just means that I'm considering infinite size network, because at each time step, I will add in one node and one edge. So when you apply the t to infinity limit, in practice, what that means is you just make t plus 1 equals to t, and then you simplify a little bit, and you end up with this expression that now is an intrinsic expression on just the degree distribution. Right? So now if you can solve this, you can get the degree distribution. And of course, that delta over there comes from the initial condition that you're adding nodes with degree 1 at each time. Excuse me. So, and you can play with this expression a little bit, and you can write it in this form, and you say that the p of k basically is proportional to the derivative of this function kp of k, which you can solve very, very easily with this type of ansatz, and you find that gamma equals 3. Right? So this is how you prove mathematically that if you do this process, the natural degree distribution will be a power law, will be a very specific power law with degree 3, which is not necessarily what you want, because most actual real systems don't have degree 3. But the fact that with a very simple process, you could already create a new network that was much more realistic and much closer to the real world than the networks people were using before, was already a very big step, and of course was somehow the trigger that started this idea of investing in the understanding and the studying of complex networks, and which of course is the reason why everybody's going to NetSci after this. So this is what the degree distribution looks like if you do it on a log-log scale. Of course, we get the straight line. And this is called the Barabasi-Albert model, which of course was later shown to be just a very simple example of something called the Yulz-Simon process that been proposed sometime in the 1920s, if I remember correctly. I'm very bad with dates. Now, of course, since we know that not all networks have degree 3, we need ways to find, and for a long time, people were trying to come up with smart ways to fine-tune this exponent. Right? We don't want it to be 3, we want it to be something that we can tune and we can adjust. And the simplest way to do this is something called the attractiveness model. Right? And now what this means is each node, this beyond its own degree, also has a value of attractiveness, as a factor of A. Right? So we're starting, if you think of it, so this is the expression for the Barabasi-Albert model, but now we're making this modification, and we say that each node gets has a slightly higher probability of getting edges than what's just by its own degree distribution. Right? So it has this A that gets added there. And of course, you can rewrite this expression a little bit by putting k plus A over there, and then you rewrite it a little bit, and you can get a similar expression as before. So you're just playing the same game as I played before. And if you think about it, I mean, it's a bit strange that just by adding a constant number to all the nodes, that this will make a big difference, right? You're just adding literally a constant that is the same for every single node in the network. But this is completely, you see that this will completely change the distribution. So you find this, and then when you solve it, you get this k plus A, so minus gamma, where gamma goes as 2 plus A. Right? And what this means is that now you have a parameter that is tuning the degree distribution. Right? So by changing the value of this A, you can tune and get whatever exponent you want. And the reason why I always show this example, following immediately the Barabasi-Albert example, is that it's a very simple way of showing you that even sometimes a very small modification of a model, by just adding a little detail or a little tweak, you can completely change the behavior of what you get. Right? Before you were stuck with alpha equals 3, with gamma equals 3, and now you have gamma equals whatever you want between 2 and 3. Now, just something I worked on a little bit a while ago, and this just to give you an idea that even, and again, very small assumptions, very small changes in your assumptions can completely modify the system. I'm going to talk a little bit about accelerated networks, which you may or may not have heard of already. And so far what you see is something like this, right? You have a network with a given average degree, and the average degree is 2 times the number of edges divided by n, and this is fixed. And of course, we saw that in the processes you're generating the network, what you have is basically you're adding n edges at each time step, so you get n times t edges, and you get n times t nodes, because at each time step you're adding nodes. And this, of course, is a constant, right? Because the t's kind of go away. Now, what happens if this is not a constant, right? What happens is if at each time step I add a varying number of edges. So instead of adding one edge at each time step, I'm adding some value, some function that is not linear in time. Right? So immediately you see that the average degree, of course, will depend on the time step I'm considering. That makes sense. Because now, if I put powers on these things, instead of being empty, it will be empty to the alpha and empty to the beta, then you simplify and you get something that just gives you a, where a, of course, is necessarily different than a. And then you expect somehow that the degree distribution will also look something like this. Right? You'll have one component that is just the usual degree distribution, and you'll have this temporal dependency. Now, of course, we know that the maximum possible degree at each time step is such. So this is actually a very clever trick. So here, what you're doing is you want to find what is the maximum, so what is the cutoff on the degree distribution. And you can do this by calculating for a given network size n, what is the probability that, or rather, what is the value of k cut, such that the probability of me having, such that the number of nodes of degree above k cut is at most 1. So this is what you're doing. So here, here t is basically n, so it corresponds to the number of nodes, and you're saying, if I integrate the time-dependent degree distribution multiplied by n, so this gives you what is the number of nodes of degree k at times t, and then integrate this between k cut and infinity, I want this number to be approximately 1. Right? So I have exactly one number, or at most one node that has that degree or higher. So this, by definition, this is the maximum degree. It shouldn't take much to convince you that you can do this and get an expression for t that goes something like this, which of course will depend on t, and will depend on the exponents that you have on the degree distribution and on the average degree. And you can do the minimum degree also such that when you normalize the degree distribution, you get 1. Right? So the degree distribution is normalized, and this gives you a way of defining k0, so the minimum degree, which you can solve and find yet another expression for that depends only on time. that you can calculate the average degree like this. So this is just your it's just k times p of k, written in a funny way. And when you do this integration between the minimum degree and the maximum degree, you get something that will go as the average degree. Of course, this has to go as t to the 8 because we kind of defined this in the beginning that the average degree distribution will go as t to the 8. And now here we have to consider two cases. If gamma is less than 2, then this simplifies in a different way. The integral is because then the limits of the integral depend very strongly on this gamma, and will tell you which regime you have to consider. So the important part is k cut over there, and you get that a, so this goes as 1 plus e plus 1, blah, blah, blah. And the total number of edges, of course, is just t to the a plus 1, which is just the average degree times the number of nodes. And what this means is that the maximum degree kind of goes as the number of edges, proportional. And So in the infinite limit, so for an infinitely large network, you have no limit to the larger degree, so you have an infinite degree network. And the degree distribution goes with this exponent that depends very strongly on the properties that you've chosen for your temporal process. Now if you want gamma that's larger than 2, then now this is dominated by the lower bound, and you can replay the same process, and you get, now that the exponent has a different expression. Yes. And again, this is to show, okay, yeah, you started with a very simple process, just preferential attachment. You tried a very small change. You added just this attractiveness value, and that completely changes the distribution. Now you try something a little bit more complex, where instead of adding just one edge or one node per time step, you're adding more, and this completely changes the process again. So, and this has been shown later. I won't talk about that here, but this has been shown later analytically that if you want to get a power law degree distribution, then you need something that is very, very close to the preferential attachment. Like it has to go precisely as a linear function. So the attractiveness of each node, so the probability that each node gets a new edge for this type of process has to be linear by definition. If it's not linear, then you destroy the system. You destroy this very fine interplay between the different mechanisms that will give you the power law. Moving on. So now now that we went through this little tangent on networks and defined a little bit what we mean by this, let's think about processes on networks. So we already see this picture, right, where you have a node and you have something happen on the node and you interrupt and things changing and moving along edges. And now you have two ways of looking at this. You can think of each node as being like a box where you have things inside. So basically, to each node, you basically assign a number or a set of numbers that describes the state of the node. And here you're just considering what's happening from node to node, or you can consider some type of object that's traveling on the node, standing on the node, and moving between nodes along the edges. Right? So you can think of this somehow as being the macroscopic level and this being the microscopic level. And the difference here is that here I'm actually my focus point is basically these little objects that are moving around, and I'm actually tracking each of them separately and considering them separately. Well, here what I'm doing is I'm just counting how many there are. Right? I'm not really interested in each one individually, just on the populations. So you can, if you think of this as being cities, here I'm tracking basically people individually, while there I'm just counting how many people there are. So you have to make a few definitions before we move on. So we're defining the sigma I to represent the state of node I. This of course can be a number, can be a label, whatever you want. The full state of our system will be sigma, will be the vector sigma that just gives us the state of every node. And of course you have some b of sigma t, which gives you the probability of having a specific configuration sigma times t. Right? If you think about it, this is a little bit of a generalization of what we just showed. Right? Before I had p of kt, so what's the probability that I have this specific set of degrees at this time? Here I'm generalizing it and I'm doing it for some configuration, where the configuration can be anything, any type of state that I can assign into individual nodes. So we've also already seen something that looked remarkably like this. This is something called the master equation. In the beginning, that shouldn't be there. In the beginning, I showed you something where you said, okay, how do I end up having degree k times t plus 1? And so the probability of having degree k times t plus 1 goes as something times the degree of having degree k times t, or having k minus 1 times t and then changing. Right? So this is the generic way, the general way of seeing this. And the saying is the variation in this probability of having configuration sigma times t basically has two terms, right? Overall possible configurations that lead to or from this state, right? And the probability that I go basically from a previous from a different configuration into this one, minus the probability that I go from this configuration to something else, times the probability of me being there already. Right? So this is exactly the same thing as we had before in the case of referential attachment. Right? Before there was only two possibilities. I either already had degree k and I stayed in degree k, or I had degree k minus 1 and then I increased my k by one step. Right? So, and this is the generic way. And so basically this is what this is saying is very simple. The variation on the quantity is how much you add to that quantity minus how much you subtract from that quantity, right? Which is the most intuitive thing in the world. So this is basically the change of the probability of having configuration sigma times t. Here we're summing over all configurations, over all possible sigmas. Here, this represents these w's at the transition probability, so it's the probability that I am in one configuration and I move to the other configuration. So in the example of the preferential attachment is what is the probability of me getting a new node, a new edge, because that's the only way I can change my configuration. Yeah, so this is so this is the idea: is if you have this configuration, you're tracking how you get into this configuration and now you get out of this configuration, right? And this gives you, with some very reasonable assumptions, basically tells you how many things are in that configuration. So what is the probability that you are in that? What is the fraction of phase space, if you want, that corresponds to that configuration? So moving on. Now, of course, if you think about it, what we have here is basically you have something called phase space, right? So with the space of all possible configurations, and you have the system moving between these configurations according to whatever rules you set the system. And so even though if you start in a very, very well-defined point in this space, the system quickly will explode and explore many configurations, right? So the most intuitive example of this is when you put a little drop of ink in a glass of water and you see the ink scattering around, right? You started with something that was very well-defined. You have water here, ink there, or ink in this very small region of water, and then as soon as you let the system go, it will explore many other configurations. Right? And in statistical mechanics, basically the way you say this is that it explores the phase states until it finds its maximum entropy somehow. Now it can define also basically averages of properties. Right? So this again is the generalization of how we calculated the average degree before. No? So here is just saying the average of property A, of whatever quantity A is the sum over all configurations of the value of that quantity in that specific configuration times the probability of you being in that configuration. Right? So it's the average, the usual definition of average, how you average something. So this is the average of T, is the value of every possible configuration and the probability of each configuration, exactly. And if you really want to do this, since you don't necessarily know all the configurations and know how to calculate these things, what you do is you list numerically many times, right? You average over many realizations, and then you see what happens. So you start the system, you numerically initialize the system in one specific configuration, and then let it evolve, and you do this many times. So, and if you do that for, if you do that for a process like the one I showed in the little animation of the nodes changing colors, you can get something like this. So you have different runs, and each run basically corresponds to a specific trajectory in this phase space, to a specific way the system evolves. Of course, since in this case, in the end, all the nodes will receive this information, all the nodes will change color. You know that if you wait long enough, they will all end there. Of course, some of them will end up there a little bit faster, some will end up there a little bit slower. But they all get there, and of course they'll get there at slightly different times. Then when you average over all of these things, then you get something that should be very close to the analytics. And we'll see that in a second. So how do you calculate the equilibrium distribution for this type of processes. So you know that you need to have something like this. This has to be true always. The variation of the population in a given state is basically how much stuff you put there minus how much stuff you take out. By definition, this is true. Now, you can also say that if you want an equilibrium distribution, you can just cheat a little bit and say the variation is 0, right? Oof. And if you think variation is 0, then you get something like this. And then you say basically the amount of stuff that I'm putting in is exactly equal to the amount of stuff I'm taking out at each time step. So they balance out and nothing changes. So of course, this is sufficient. It's not necessary. There might be other ways in which you can just achieve the same result, but this is the standard one, and it's of course sufficient, so we use it. And this is something called detailed balance, and because it's the idea that what you put in, it balances exactly what you take out. So you can rewrite this expression in a slightly different way. And this basically ensures that you get a convergence to an equilibrium distribution. And you can use this basically as a way of choosing how to evolve the process, right? How the process changes. Because you can just say, if you can basically calculate what's the probability of going from one configuration to the other. Now, another thing you can consider is you can also have something called an absorbing state, right? And this is something we saw in the plot before. Is at the end, all the nodes have changed colors, and after all the nodes have changed colors, nothing happens, and you can never leave this state. So after you reach this state, you can never leave. So this means that you can get into here, but so you have stuff coming in, but there is nothing leaving. So that's what we call an absorbing state. So in practice, how do we actually do these calculations? So there's in many cases, what you have to do is you have to use something called the mean field approximation, where you assume that there are basically no correlations. So things are really not, you don't have too much structure in the system. You're assuming that all the elements in the system somehow are interchangeable, so this is called the homogeneous assumption. And this is where it's called the mean field, is that each node or each element in your system somehow isn't sensitive to its exact local neighborhood, but somehow feels an average overall over the whole system. Right? And if you do this, then you can basically simplify this a little bit, and then you say that the probability of having a specific configuration is just the product over the probabilities of each node being in that specific configuration. Right? So here, basically ignoring all possibilities of contact between nodes directly. And you're also defining, by doing this, what you gain is something called local dynamics, right? And what this means is that the probability or the transition rate between one configuration and another basically only depends on the transition rates for the individual nodes. So everything is local. So the transition, so for node I, the transition rho between going from configuration from one configuration to the other depends only on the small number of possible other nodes. You can also define, of course, so now, like I showed you the picture, you have the microscopic view and you have the macroscopic view, and you can, of course, move from the microscopic to the macroscopic by basically integrating things, right? So this is what I'm showing. Here, so I'm defining, okay, what is the macroscopic quantity? So n of x, let's say, times t. Here we go. So basically what you're doing is you're summing over all configurations over there. You're summing over all the nodes. And you're using this delta function to basically say, to only count the ones that correspond to the quantity you're looking at. And so if this is 1 if node I is in state X, and it's 0 if node I is not in state X. So that way you're only counting the states that have the configuration you want, so you can calculate what it is. And this, of course, will just tell you how many nodes there are in state X. And of course, you can also write like a macroscopic master equation where you only consider macroscopic quantities instead of focusing very detailed on these microscopic ones. Which of course will follow the same rules as you did before, but now only macroscopic quantities are included. So let's look at the simple system instead of just focus of me boring you too much with all this theory. So this is the simplest, possibly the simplest system. It's called a reaction system, right? You can think of this somehow as a chemical reaction. You have atom A comes in contact with atom B, and with some probability it becomes 2. Now you have to define all the transition rates. So of course, the probability of you going from A to A given that you are A is 1, of going from B to B given that you are B is 1, and going from B to B given that you are A is 1. And so this means that you have all of these states that are absorbing, and once you get there, nothing happens, and you always go there. And the one that we're interested in is what is the probability that you switch from A to B, given that the guy you're interacting with is B. Right? So it's lambda, which of course is that rate over there. And so if you are A, you will become B, so that there's to B over there, by coming in contact with the B. Right? So you go from A to B, given that you talk to a guy in B, and that has probability now. So B is basically an absorbing state in this system, right? You can go from A to B. Once you are B, nothing changes. So, and that's basically what's represented here. If you go from B to B, if you interact with the B, you go from A to A, you interact with an A. So these two are stable, and if you are B, you never stop being B, even if you interact with an A. So now you can write this funny looking macroscopic equation, which is exactly similar to what we had before in spirit. You're covering the variation on this quantity and B, so the number of P atoms as function of T. You have to, of course, to count to sum, like we saw before, overall configurations, overall the nodes, and basically counting yes if that node is in state B or not. And then since we have an expression already for the DOP of sigma T, so the probability the variation probability for the state is in state sigma times T, which is this funny looking expression. And this is basically just the microscopic master equation. So what I'm showing here is basically the macroscopic master equation is basically an integration over the microscopic master equation. Let's put it over there, and then you can start doing these calculations. Of course, you know you have some normalization conditions. If you sum overall configurations, then the rates have to equal 1. And if you have, and you also know that the probability of you transitioning from sigma from whatever state to another state basically to be given the state of the person you're interacting with basically has to go like this. And when you make these substitutions, you get something that's much, much simpler, and again, would only depends very strongly on basically how you define the process, and mostly on, this is still an intermediate step, so you still have some microscopic quantities, but you can see already that most of them are already left. So if you continue the calculation, now you apply that mean field approximation, right? You define average quantities. So now you're saying the fraction of the average number of things A is the number of particles in state A divided by the number of particles. Probability of being state B is the number of particles B over n. So what you're saying that basically each particle is completely indistinguishable, and the probability that it is one state or the other is just the fraction of particles that are in one state or the other. And the probability of being in a given configuration is just the product over all the microscopic configurations. when you do this, then you can simplify this expression a little bit. Because this is basically saying that A is connected to B. And so you're starting in this configuration where you are A, and you're transitioning to this configuration where you are B. This would be lambda if it is connected to B. If B is connected to B, this is 1, and nothing basically nothing happens. And finally, you get so. I should do this. But now, of course, you need to know what is the probability that you are connected to a B or the probability that you are connected to an A, right? And that's where the next step comes in. So probability that at least one neighbor of I is B, right? You know that each node has, you can assume, let's say that each node has degree K, or node I has degree K. What is the probability that at least one of those neighbors is B? And the way you do this is basically you ask what is the probability that none of the neighbors are B, and you subtract this from 1. So the probability that each one of them is not B is 1 minus B. You need to do this K times, so this is the probability that you have nodes of connected nodes of K, and then you in state B, and then you just subtract that from 1, so it's the probability of having at least one of them. When you put that in the equation, then you get the final macroscopic master equation that depends only on the macroscopic quantities, which of course in the limit n(b) over n smaller than 1, what this means is in the limit where you have very small numbers of b, so at the beginning of the process, if you want, you can simplify this a little bit and you can solve it. So this is basically called the homogeneous mixing approximation, right? So this is something that we're going to use a lot depending on the process. It basically assumes that everybody is in contact with everyone. The probability of your neighbor being in one state or the other basically comes just from the fraction of nodes in the system that are in that state. And of course, and then you can solve this and you can see immediately that if t goes to infinity, this will basically go to n. So all the nodes will end up in state B. And we're the expected that because B is an absorbing state. Once you get there, you always stay there, and you have a flow from other configurations to that configuration, so you always end up there, and all the nodes will go there. So there we go. So now the fun part begins. Can you actually read this? So basically what this is doing is it's running this reaction process in a very simple network. So in this case, it's an Erdős training network, and it's plotting as a function of time basically what is the state of each node. So blue is A, B, red is B. So you can, and this is running right now completely stochastically with using random numbers. So you can see that in this case, node like 18 or something started in state B, so there was just one node at the beginning, and the process ran, and eventually you started seeing other nodes switching from A to B, because at each time step you check and see if any of them changes it. And you can see that, of course, after a while, they all become red. Now if I kill this and do it again, you'll see that it will be different. And now it started in node, I don't know, like 45 or something, and then it went, and then after a while, everybody turned B, and once everybody's B, they'll stay there forever. Right? So if I close this window, we will continue. You know, for some reason the windows are opening here instead of there. Okay. So this is the infection time for each node. So at what time that node was infected in the process. So at each time step, like we saw, it started over here. That was the first one, and then it went there, there. So you can see how it's jumping from node to node. And then if you close this, and now what I'm doing is I'm doing basically 100 runs of this process, and I'm plotting for each of those runs basically how many nodes there are in state B. And you can see, of course, that in some cases B goes very quickly, in some cases it goes very slowly. So it takes a long time to get enough mass because everything's stochastic. And then when you do, and like we saw before, if we want to see what is somehow the average behavior of the system, you can just average over all these trajectories. So I can close that. And now if you compare the average trajectory with the analytical one, you can see that it's very close. Right? And this, of course, I'm doing in a very small system with just n equals 100. I'm just doing a few runs, so there will be always a difference. If you do more runs or larger systems, you'll get much, much closer. And this is using an Erdős-Rényi network. Now, one network I didn't really mention too much because analytically it's not that interesting, is something called the West-Strogatz network, right? And here what you have is basically you have a ring, and each node on the ring is connected to k nearest neighbors, and then you rewire this network in probability P so that you create shortcuts between them, right? But the idea is, for the West-Strogatz network, you have something that's very regular, right? Each node is connected exactly to k neighbors, and yes, so it's very regular, so each node is connected in neighbors, so it's likely that the assumption of homogeneous mixing, where everybody is connected with everyone, everybody has the same probability of being connected to a node that is in state P, probably will not be very valid. So we can rerun this game with the West-Strogatz network. And here we go. And now you see a picture that's completely different, right? Immediately. Let me go here so I can actually see. And you see this very distinct pattern, and this corresponds basically to the structure of the network, to the connector, the nearest neighbors. Right? If you are here, depending of course on the parameters you're using, but in this very regular regime, you can't jump there, right? Because there is no connection between node 20 and node 40 or node 60. You only have nearest neighbor connections, local connections. Right? So you have to jump to one of the neighbors, and then you explore that neighborhood a little bit, and then you jump maybe to another neighborhood, and then you explore that neighborhood a little bit, and that's why you see these little branches, right? These little mini fires happening there. And then eventually you will, of course, reach everywhere, because it has to reach everywhere the network is connected, blah, blah, blah. But you can see that the pattern is very different, right? Because here we are explicitly breaking the homogeneous assumption. Right? The network is not homogeneous, there are very strong correlations. You can only talk to your neighbors, and your neighbors are very limited to where they can be. So this again is the infection times, and you see exactly the same pattern, right? You start in a specific neighborhood, and then you jump to another neighborhood, etc. And of course, these distances here correspond more or less to the degree that you're using. And You can see that I'm running again 100 runs in the background. And again, you get 100 different trajectories that kind of look the same, right? It starts at 1, it's here, it's something that at one node with it at state B, you end up with all the nodes at state B, and you get there in some way. But now, if you close this and you look at the average, you get something that's very, very different. Right? And no matter how many runs you make or how big the system is, these two lines will never be on top of each other. And the reason for this is like I was saying, because we explicitly broke the homogeneous mixing assumption. And we were assuming that all nodes were the same, all nodes were more or less connected at random, but this is clearly not the case. You have very well-defined neighborhoods, you have very strong correlations between neighborhoods, you can only connect in very specific ways. And since our assumption in our calculations was wrong, then our result was wrong. And of course, you can say that the difference maybe is not that big, and maybe you are happy with this difference and it's enough for what you need, but you have to be careful about what assumptions you're making when you're doing the calculations or even when you're doing the simulations, and what the process actually is, right? Because the two might not match. And this is why I always like to work through and bore you to death with this calculation of the of the master equations and actually calculating everything explicitly and telling you exactly what are the assumptions I'm making, because then I want to break them and so that you can understand why it's important to understand this. Now I think we're getting ready for the coffee break. If I'm not completely crazy.
Excuse me. So you are not rewiring any edges in this?
I think I'm rewiring with some small probability. Oh. So not too much, because I don't want to break the symmetry of the system. I can give you the code if you want, actually. Yes. So this is just a piece of the code where I'm actually changing, where I'm basically doing the process. You can look at this in more detail later if you like. And since we're getting ready for it, let me just finish this. So now this is a more detailed view on what I was just telling you. So you have this is the process, because the network basically is completely disorganized, and you have a very well-defined distribution, and this works pretty well. And then when you have something like this, where the network is much more structured and much less random, then the system breaks, right? So I don't remember exactly what is the value of p that I'm using, but it's a small value. So it's somewhere around here. And then you have exactly this type of behavior, which of course breaks it completely. And this is about the assumption, so you can compare the two. When you're making this assumption here, gradient, and that's it. Yes, and I think we can stop here for coffee, because I think it's more or less on time, and then I'll start with random walks afterwards. So thank you so much.
So now we have time for the coffee break.